Hello friends, in this lecture we are going to study the possible opportunities in the sense both technical and financial opportunities of the local distributed energy sources and the microgrid. So before going to the potential services and opportunities, we will see the structure of the power system. So nowadays we have the grid structure like this. On top here the LV level. In contrast to this, the active distribution system, which is shown below, is it has bidirectional power flow. The power flow can be from the distribution side to the HV side also. So bidirectional flow is possible here, and technical services are provided by distributed energy resources at HV level, MV level, and LV level. Now, what are the possible services that can be provided by the sources in MV and LV levels, or in general from the distribution level? Before going to the services, the whole distribution system is operated and managed by the DSO, and here the transmission system is operated and managed by the TSO, and this is the central generation pool. Okay, now the services can be frequency support, voltage support, then peak load and power loss compensation, islanding and black start support service, balancing power supply service, etc. So for these technical services, the resources or the owner of the resources are incentivized, and if there is a problem with the system and whoever contributes to the power pollution, he or she will be penalized. So to incentivize and penalize, we have to identify the resource properly. So to do that, it's very difficult. So one assumption can be the technical services that is provided by the distributed energy sources in the LV level is restricted to the LV level only. Similarly, at each voltage level, the services provided at that voltage level is restricted to that particular voltage level only. That is one assumption which is used in many of the papers. But this is of course not realistic, as we know that a technical service that is provided at the LV side will reflect the HV side also, right? Because if there is excess active power this side, it can be pumped to the MV side, and if there is excess active power here, it can be pumped to other microgrids, right? The neighboring microgrids also, it can be pumped to neighboring microgrids also. So this is not a realistic assumption, but for incentivizing and penalizing sources, this is theoretically used. That's all. So we need a proper, an organized framework for the local energy market inside the distribution system, where the power is sourced from the sources, the generation sources, and it is provided to the buyers or the end consumers. In the MV level, it can be industrial consumers also. Okay, now we'll see how the reward management is done. So for reward management, we have to identify the stakeholders first. So these are the stakeholders: the DSO, the distribution system operator, then the end consumer, then the energy supplier. Now, what are the potential risks posed to the these stakeholders? For the DSO, of course, load increase is a potential risk. This load increase can be long term also, because after 3 years, if the load demand is going to be increased in the system, then the DSO has to invest on infrastructure expansion and planning, accordingly. So this is one risk. Then for the DSO, supply interruption is also a risk, because technical feasibility, everything related to technical feasibility is the responsibility of DSO. So supply interruption actually affects reliability of the system. That is also DSO's responsibility. So that is another potential risk. Then for the end consumer, supply interruption is a problem, because he doesn't get power. He doesn't get energy when required. Then price volatility. Increase in price is a risk for the seller, or the increase in price is a risk for the end consumer or the buyer. So and decrease in price is a risk for the supplier. So the supplier can diversify his portfolio, his energy portfolio, so that multiple sources can be used, and he can fight against the decrease in prices. Okay, that can be done. Suppose he is using a diesel generator and the cost of production is high because of the price of fuel, price of diesel, then he can switch to other generation sources. He can invest on other sources. And the end consumer also, if the end consumer's retail tariff is high, so he can fight against the spike in retail tariffs by installing his own rooftop solar PV or a micro wind turbine or a small fuel cell, whatever. So these are the potential risks and how to hedge these risks. Now, going to the energy and cash flow under arbitration, let's see an example here. Here a microgrid, a grid connected microgrid is shown, where the local loads are 70 kilowatts and 50 kilowatts. The total is 120 kilowatt hours. Now, the total generation here is 250 kilowatt hours. So locally, this 120 is fed from these two generators, these two local generators. So 250 minus 120 is 130. So the excess energy 130 can be pumped to the grid. But the loss in the local system is 10 kilowatt hour. So 120 can be pumped to the grid or backfed to the grid. So this is known as the backfeeding capability of the microgrid. Now let's see how the cash flow, the direction of cash flow. So here the DSO is a third party. The DSO can be a third party, or the third party can be called as an aggregator also, or a microgrid central controller also. So sometimes he takes the role of technical and financial management. Sometimes it is segregated. Technical management is taken care of by the DSO and a separate aggregator would be there. That depends on the market framework. So here let's take it as a third party who manages both the technical and financial management of the microgrid. So in this case, you can see the energy is bought by the third party from the sources, these two local energy sources, at the rate 0.12 euros per kilowatt hour and 0.1 euro per kilowatt hour. So the total amount that is purchased is 150 and 100. So accordingly, 15 and 12 is the expense. So 27 euro is the expense of the third party. That is, cash outflow is 27 euros with respect to purchase of energy from the suppliers. Now, this 120 kilowatt hour should be provided to the end consumers, right? So that is at the rate of 0.15 euro per kilowatt hour and again both are 0.15 euro per kilowatt hour. So the total expense here is 10.5 plus 7.5, which is 18 euros. So the cash inflow, this is not expense, this is earning. Okay, this is because the energy is sold, right? So this is earnings. 10.5 plus 7.5 is 18 euros, which is the cash inflow to the third party. So here 27 euro cash outflow and 18 euros cash inflow. Now 120 kilowatt hours is backfed to the grid, right? For that there is cash inflow to the third party, which is and this power is sold at 0.13 euro per kilowatt hour. So the total is 15.6 euros. So this is also cash inflow. So the total cash inflow, net cash inflow is 15.6 plus 18 minus 27, right, which is 6.6 euro. So gross profit for the third party in this case is 6.6 euros. Now we'll go to specific examples and case studies where technical services are provided. The first example is for peak shaving. And here two examples are given for peak shaving. One is with respect to load reduction and the second one is with respect to generation reduction. So in the first case, the power flow is from the upstream grid to the local generation site or the local node. This is the local node. Okay. Now 10 kVA is the maximum power carrying capacity of the line, but as of now it is 150% overloaded. And this generator is not connected. Okay, so there is a local load which is 15 kilowatts, so that is completely fed from the grid. So this is 150% overloaded. Of course, here we assume unity power factor. That's why we are able to compare this kilowatts and kVA, and we can say that it's 150% overloaded. So in the second case, what happens is we are slowly connecting this generator into the system, this local generator into the system, and we are stepping up the generation from 0 to 6 kilowatts. So out of this 15.6 is locally fed. Now remaining is 9. So 9 comes from the upstream grid, right? So now it's only 90% loaded. So if there is a if there is a 10% tolerance for this line flow limit, then that is satisfied now. It is only 90% loaded. Earlier it was 150% loaded, right? So when looking from the upstream grid side, what happens is that the effective load has reduced because the effective load is now 15 minus 6, which is 9 kilowatts when looking from the grid side. Earlier it was 15 minus 0, which is 15 itself, right? That is what is written here, load reduction. So by means of load reduction, we are trying to shave the peak. Now, in the second example, we have 15 kilowatts local generation and 1 kilowatt is the local load. So 14 kilowatts active power is in excess and 14 kilowatts is pumped to the upstream grid. So that's why this is 140% overloaded now. Now in the second case, the generation has come down to 10 kilowatts, then load is still 1 kilowatt. So now the excess generation is 10 minus 1, which is 9 kilowatts. So 9 kilowatts is pumped to the upstream grid, and that's why this line is now 90% loaded. So when looking from the grid side, the net generation from the local generation side is 15 minus 1, which is 14. So 14 is the generation when looking from the grid side. So but in the second case, when you are looking from the grid side, the local generation is 10 minus 1, which is 9. So there is a reduction. That is what is written here, generation reduction. Now we'll move on to the next service, which is voltage regulation service. 1 second. Okay, now here also two different cases are shown. In the first case, we have power flowing from the upstream grid to the local node here, and in the second case it flows from the local node to the upstream grid. First we'll see the the figure on the top. So 100 kilowatts is the local generation, 500 kilowatts is the active power load, and 200 kVAR is the reactive power load. Now 100 minus 500. So basically here what happens is 400 kilowatts extra is needed from the grid side, right? 100 is already fed from the local generation. So this is the power flow direction. Now, because of this current flow in the line and the drops, the corresponding voltage drops, the voltage profile at the local node is 86.1%. Now we are trying to control the reactive power from the local generation side by increasing the local reactive power generation from 0 kVAR to 200 kVAR. Now the voltage profile has improved from 86.1% to 88.6%. Now, in addition to the reactive power, local reactive power compensation, we are going for active power control also. So for active power control, the local generation has been increased from 100 kilowatts to 200 kilowatts. Now you can see here the voltage profile has further improved and it has become 91.8%, which is in between 90 and 100% and within the 10% tolerance limit. So this is another example of providing voltage regulation service by means of reactive power control and active power control from the micro sources. Now in the second example, we have 700 kilowatts of local generation but 50 kilowatts of load. So there is excess generation and 650 is pumped. Actually, when it reaches here, the loss must be reduced. The loss must be deducted. But anyway, if loss is discarded, if it is assumed to be 0, then 650 is reaching here, right, to the upstream grid. Now, at present, the voltage profile at the local node is 114.1%. Now it is violating the tolerance limit of 10%. Then it should be actually in between 100 to 110, right? In between 100 and 110, but now it is 114.1%. So we are trying to control the reactive power from the local node side, or reactive power injection at the local node is updated now by having a consumption of reactive power of 200 kVAR. That is, if this source has a power electronic interface or an inverter having reactive power control capability, then it can operate in lagging power factor mode, and this 200 kVAR consumption can be 200 kVAR can be consumed from the local node. So because of this, the voltage has been reduced to 112.2%. The load is untouched. Now again, we are trying for active power control, similar to the case which we have seen above. The only difference was the direction of power flow. Here the direction of power flow is towards the upstream grid. Now from 700 kilowatts, the active power generation, the local power generation at the local node is reduced to 500 kilowatts. So again, you have a reduction in voltage, and it has now become 108.2%, which is within the 10% tolerance band. That's what is the voltage regulation service. Now coming to loss reduction, you can see three different figures here. In the first figure, we have both active and reactive power flow in the same direction, that is towards the local node from the upstream grid. Now the loss is 0.43 kilowatts, and the local generator is not connected. So the total load is completely fed from the total load demand is completely fed from the upstream grid. Active power demand is fed from the upstream grid. Now here we are going to connect the local generator, and 30 kilowatts of active power is generated locally, and 20 kVAR of local reactive power is generated from here. So out of this 40 kilowatts, 30 is fed locally and 10 will come from the upstream grid. Of course, some losses are there, but in general, the direction is towards the local node. So P flow has reversed. Now, what about Q flow? 20 kVAR is generated locally, but 10 kVAR is the reactive power demand, local reactive power demand. So we have excess reactive power at the local node side. So the Q flow has also reversed. It is towards the upstream grid now. Now, in the third case, actually, we are trying to control active power and reactive power from first and third cases, and we want this mode, this condition, the figure in the middle. Okay, so in the third case we have loss 0.33 kilowatts, where 30 kilowatts is the active power generation and 20 kVAR is the reactive power generation. Now if we initially the load is disconnected here. When the load is connected, what happens is the P flow towards the upstream grid, that is going to be reduced because 40 is here, right? So in this case 30 kilowatts is going to be going to the grid. In this case only 10 is coming from the grid, right? 10 is coming from the grid. In this case 30 is going towards the grid. So that also reduces the loss because of connection of this load. The loss is reduced to 0.05 kilowatts. So basically here two cases are there. One is 0.43 kilowatts to 0.05 kilowatts loss reduction because of the connection of this incoming generator, and another case is the reduction in loss from 0.33 kilowatts to 0.05 kilowatt because of the connection of the load. So that is the service of loss reduction. Now in the last case, reliability improvement. How to improve reliability with the help of local generation or local load, or in general broadly with the help of a microgrid. So in the first case we have a storage device, but the storage device no output from the storage device. Initially there is no output from the storage device, but we have two local loads, 25 kVA load and 15 kVA load. 20 kVA is the local generation. So but total load is 40 kVA. So the remaining is taken from the upstream grid. Now when the system is completely islanded, the whole system is islanded, this switch is off, so the whole system is islanded. Now this is active, this storage device is active. So 30 plus 20 is 50 kVA, right? 50 kVA is there, but this 30 is capacity. Total load is 25 plus 15, which is 40. So 20 is coming from the local generator. 20 can come from this storage device. 30 kVA is the total capacity. So 20 can come from this storage device. So in islanded mode also, generation demand balance is satisfied. Now in the third case, what happens is, that is partial islanding case. This is partial islanding. If in this case two loads are there, 25 plus 15, 40, 20 kVA generation is there, local generation is there. So total load cannot be met from the local generation. So extra power should be tapped from the upstream grid. In this case, we cannot fully island the system as we don't have a storage device here, because if we totally island the system, then 40 will be the demand and 20 will be the generation. There is no normal operation then. So what we are going to do here is partial islanding. That means this segment is only, and 50 kVA generation has become 15 kVA and 15 kVA load is already there. So it is fully fed from the local generator, and this load is disconnected. And here also it is disconnected. So basically electrically this part is isolated and we can continue the normal operation. But of course at the cost of reduction in reliability, because this load is not fed. So that's all with the services, potential services that can be provided by the local generators and distributed energy sources in the microgrid. Thank you.